Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. We are GROUP32 and we will be presenting about project Vertical Farm Aquaponic. Our group members are me, Muhammad Dina Hakim bin Mawar, Ryan Joshua Yonatan, Muhammad Adam Farhan bin Muhammad Aziz, and Irfan Mushid bin Suhaiman. Okay, let us start with the introduction. This project presents a stimulated smart farming system developed using the Arduino Uno Tinkercad. The system automates essential environmental controls in a vertical farm aquaponic setup. By integrating sensors and actuators, it continuously monitors temperature, soil moisture, and light intensity, then responds automatically to maintain ideal growing conditions. The system uses a water pump, RGB, LED, buzzer, and grow light to make real-time adjustment based on sensor reading, while a 16x2 LCD provides live feedback to the user. Structured programming techniques such as modular functions and clear decision-making logic are applied throughout the control system. Overall, this project demonstrates how automation improves consistency, reduces manual labor, and supports sustainable agriculture practices in modern precision farming.
So now I will be explaining how our system works based on the general flowchart. So first, the program begins by initializing all the important components such as the LCD display, the serial monitor, the input sensors, and the output devices. Once everything is ready, the system enters the main loop, which keeps running continuously. Inside this loop, the Arduino first reads all the sensors, including the temperature sensor, the soil moisture sensor, and the LDR for light intensity. The readings are then converted into actual values such as degrees Celsius and percentage. These values are displayed on the LCD and also printed to the serial monitor for the real-time monitoring. So the system calls three main control functions. The first function is control RGB LED. This function checks the temperature value and decides which color the RGB LED should display. For example, if the temperature is below 25 degrees, the LED will turn green and the buzzer stays off. But if the temperature is between 25 to 37 degrees, the LED turns yellow. But if the temperature goes above 37 degrees, the LED turns red and the buzzer activates to warn the user. The second function is control motor, which controls the water pump based on the soil moisture level. If the soil moisture is 30% or below, the pump runs at full speed to water the plants. But if the moisture is between 30 to 60%, the pump runs at half speed. And if the soil moisture is above 60%, the pump turns off to prevent overwatering. The third function is control bulb. These functions check the light intensity using the LDR. If the light level is 40% or below, the bulb turns on to provide extra light. But if the light is above 40%, the bulb turns off because there is already enough natural light. After all actions are completed, the systems wait for 1 second, and then the loops will repeat. This allows the greenhouse to be monitored and controlled continuously in real time. So overall, the flow charts shows how Arduino reads the environment, make decision, and automatically adjust the pump, lighting, LED indicators, and also buzzer to maintain ideal condition for the plant growth.
Good morning everyone. Today I will be presenting the code for our project titled Farm Aquaponic Greenhouse. Our system uses Arduino to automatically monitor and control temperature, soil moisture, and also light intensity. We also output components such as DC pump motor, RGB LED, buzzer, and grow light. These scripts explain how our code works part by part. Firstly, the library and group information. The code starts by including the Adafruit liquid crystal library, which we use to control the 16x2 LCD display. And then at the top of the code, we include our group member's name, the date, and our project title. The pin definitions, we define all the pins used in the project. Firstly, A0 is the temperature sensor, A1 is the soil moisture sensor, A2 is the light sensor on the LDR. The motor is connected to 3 digital pin. The buzzer is on pin 5, the RGB LED use pins 11, 12, and 13. The growth light or bulb is connected to pin 7. We also create the LCD object to control the display. Setup section function, we start with the serial monitor for debugging. We all set sensors as input and all actuators as output. We initialize the LCD as a 16:2 display and turn on the backlight. The startup message Aquaponic system is shown briefly before clearing the screen. For the loop section, inside the loop, the system continuously reads data, displays it, and controls the actuators. For the reading sensors, we read three main sensors, which is the temperature sensor. It allows to give a raw analog value. Second one, soil moisture sensor. It also gives a raw analog value. And also light sensor, the LDR. There is a raw value is converted into light percentage using map function. For example, higher LDR values, which means a darker environment, and a higher soil moisture analogs, which means a wetter soil. For the temperature calculation, we convert the temperature sensor reading into degrees Celsius. The raw analog value is turned into millivolts, then it converts into Celsius using this formula, voltage minus 500 times 0.1. This gives a stable temperature reading. For displaying the LCD, we display the temperature on the first line and the soil moisture percentage on the second line. This allows real-time monitoring of the environment. The actuator control function, there are three custom functions that control the system. Firstly, the control RGB LED temperature. This part is coded by Adam Farhan. The RGB LED shows temperature status, which is below 25, it will shows green color. 25 to 37 degrees Celsius, it will show the yellow color, which is safe zone. And also above 37 degrees Celsius, which is red, and buzzer will on. This gives a clear visual and audio warning. For the second part, the control motor for moisture. This part is coded by Muhammad Daniel Hakim. This motor behaves based on soil moisture. From 0 to 30%, the motor will have full speed. From 30 to 60%, the motor will have half speed. And above 60%, the motor will stop. This stimulates automatic irrigation. For the last part, control bulb LDR value. This part is coded by me, Ryan Joshua. The grow lights turn on and off based on the light level. If the light is low, it's below 40%, and the light will on. If the light is strong, then the light will off. This helps to maintain a proper lighting for the plant growth. For the loop delay, we add 1 second delay to the system every second without lag. For the conclusion, our code reads all time temperature, moisture, and light levels, displays them on the LCD, automatically controls the monitor, RGB, LED, buzzer, and grow light, helps create a stable environment for plant growth in our aquaponic greenhouse. Thank you. For our aquaponic system, we use the combination of sensors and actuators connected to the Arduino. First, we have three analog input sensors, which are the temperature sensors on A0, which reads 0 to 5 volts to measure the temperature, the soil moisture on A1, which converts the voltage into a moisture percentage, the LDR on A2, which detects light levels and converts them into percentage. Next are our output. The water pump on pin 3 uses PWM with values from 0 to 255, allowing us to control the speed depending on the moisture soil. The buzzer on pin 5 is digital, meaning it is simply on and off for high temperature alerts. For status indication, we use an RGB LED on pins 13, 12, and 11. Each pin uses PWM to adjust the brightness of red, green, blue colors. We also have a grow light bulb on pin 7, which turns on when light levels are low. Finally, the LCD display communicates using the I2C pins SDA and SAL to show the temperature, soil moisture, and also system status. Overall, these components work together to fully automate monitoring and control in our aquaponic greenhouse.
Now I will show you the Tinkercad circuit for the aquaponic greenhouse that we has made. In the circuit, we have three types of sensor. That is the photoresistor sensor, soil moisture sensor, and also the temperature sensor. Other than that, we also have other equipment, other components such as LED RGB, the buzzer, LCD, the motor for the pump and also the power supply. So now I will show you the demonstration of this tinker card circuit. So as we know, we have three types of input sensors. As we have the input sensors, we also must have the output sensors also. So the output sensors in this circuit is the buzzer, the RGB LED, the DC motor for the pump, and also the light bulb. So let me start the simulation. As you can see, we have other components also in this circuit, that is the power supply that shows the volt that we use, and also the LED that shows the temperature in Celsius and also the soil humidity in percent. So first, I will show you how the temperature sensors function. I will change the temperature a bit. So as you look, the temperature now is 18.9 Celsius. And the RGB LED will turn to green, and the buzzer is still off. This will occur when the temperature is less than 25 Celsius. Next, I will increase the temperature a bit. So, the temperature now is 25.8 Celsius, and the RGB LED is turned to yellow, and the buzzer is still off. This condition occur when the temperature is between 25 to 37 Celsius. Lastly, I will increase the temperature. So as you can see, the RGB LED turn to red, and also the buzzer is on. The temperature now is 62.9 Celsius. This condition occur when the temperature exceeds 37 Celsius. So next, I will show you how the photoresistor sensor functions. So when the LDR level is less than or equal to 40, the light bulb will lights on. For example, I adjust the light. So as you can see, the light is on. This is because the LDR level is less than or equal to 40. What if I change it a bit? So as you can see, the light bulb is off. It is because the LDR level is more than 40. Lastly, I will show you how the soil moisture sensors functions. So I will change the soil moisture sensor. As you can see, the soil moisture percent is 3%, and the motor move at 2846 RPM. It is because this occurs when the soil moisture is less than 30%. This will make the motor of pump full speed with the PMW value of 255. Next, I will change the soil moisture sensor. So as you can see, the DC motor for the pump move a bit slower. That is 1300 to 1400. The soil moisture percent show 59%. So these conditions occur when the soil moisture is between 31% to 60%. This will make the motor pump is half speed with PWM value of 128. And I will change the soil moisture for the last time. So as you can see, the DC pump stop moving and the RPM is 0. The soil moisture now is 93%. So this condition occur when the soil moisture is more than 60%. The motor pump will shut down and the PWM value is 0. So that's all for the demonstration of the circuit.
So let's move to the conclusion. The vertical farm aquaponic greenhouse project successfully demonstrated how structured programming and system interfacing can be applied to create an automated and sustainable farming environment. By integrating sensors, actuators, and decision-making logic, the system effectively monitored and controlled temperature, soil moisture, and light levels to maintain optimal conditions. The use of modular C++ programming, combined with real-time feedback through the LCD and safety features such as RGB, LED, and buzzer, showcase the system's reliability and efficiency. Overall, this project highlights the potential of low-cost automation to improve resource management, enhance environmental stability, and support modern vertical farming and aquaponic practices.